This is example 2 in module 6. In this example, I've got two EMFs in this circuit. We're basically asked to calculate the current through and the voltage across all the resistors in this circuit. And I've got two EMFs. So it turns out that I can't combine these resistors into a single effective resistance because they're not all connected in series or parallel. Now, clearly these two are connected in series, so I could combine those, and these two are connected in series, so I could combine those, but those are not connected in parallel or series with R3 because I have this EMF here. So what I'm going to have to do is apply Kirchhoff's rules. So I'm going to apply Kirchhoff's rules to this circuit. The first thing that I need to do when I am applying Kirchhoff's rules is I need to identify how many unknown currents I have. Because Kirchhoff's rules are going to allow me to write down a system of equations that I can solve to determine the unknown currents. So I'm going to have a different current on each branch, and each branch in a circuit is basically the wires that connect junctions. And I have two junctions here, right? I've got 3 wires that connect here and 3 wires that connect here. So I've got current that could run through this top branch, current that could run through this middle branch, and current that could run through this bottom branch. All 3 of those could be different currents, and so I have 3 unknowns. So the first thing I want to do is determine how many unknowns I have. I have 3. The reason that I want to know how many unknowns I have is so that I can determine how many equations I'm going to need in order to solve for these unknowns. Alright, now for each unknown current I need to draw an arrow that indicates the direction that I'm going to assume the current goes. I do not have to know what direction the current is actually going to go. If I pick an arrow that points to the right here, I call this current 1. If I get a negative number for current 1, it just means that the actual current runs in the opposite direction that I have drawn, which is fine. So really I don't need to worry much about getting the direction of these arrows correct. I just need to worry about picking a direction and then calculating the potential differences across the resistors correctly. So here's another arrow for I2, and here's another arrow for I3. So clearly one of these currents at least has to be pointing in the wrong direction. I can't have all of the current in the circuit running towards the same junction. So one of these currents is going to have to be negative, but that's fine. All I need to do is pick a direction, draw an arrow, write down a label for it. So I've got currents 1, 2, and 3. The next thing I'm going to do is I'm going to write down loop rules for all of the interior loops. So we have 2 Kirchhoff rules. One is the loop rule, one is the junction rule. If I only use interior loops for my loop rules, then I won't accidentally create a system of linearly dependent equations. And if you don't know what a system of linearly dependent equations is, then that means you don't know how to make sure you don't generate a system of linearly dependent equations. And so what you need to do is you just need to follow these rules. This is not the only way to solve the problem. But if you do it this way, you're not going to accidentally set up a system of equations that can't be solved. So I have 2 interior loops. Interior loops are loops in the circuit that don't have any wires that run through them, right? So it doesn't have a wire that runs across it. I've got a top loop and a bottom loop. The other loop in this circuit that I could identify as a loop would be this outside loop. And this outside loop is not interior because it has a wire that runs through it. And I do not want to use that loop when I write down my loop rules. So let's use the top and the bottom loop and write down the loop rules. That's going to give me 2 equations. I have 3 unknowns, so I'm going to have another equation to solve for these 3 unknowns. Alright, I'm going to start at the bottom left-hand corner of this top loop, and I'm going to go around it clockwise. So loop rules. Alright, so I go around it clockwise. Everything I run into that is a circuit component, I need to calculate or write down what the potential difference across it will be. When I run into EMFs, it's easy. So the first one I run into is the EMF 1, and I'm going from the negative side to the positive side, so I'm going to get an increase in the voltage. That's plus EMF 1. The next one I run into is this resistor 1, and I'm going through that resistor from left to right. That's in the direction of current, and that means that the potential is going to decrease. Again, it doesn't matter if I get the direction of this arrow correctly. It only matters that once I have my arrow drawn, when I go through resistors in the direction of the current that I have drawn, I write down a negative change in potential, and if I go in the opposite direction of the arrow I have drawn, I write down a positive change in potential. So I'm going through resistor 1 in the direction of current, so that should be a negative I1 R1. This is just Ohm's law applied to that resistor. The next one I run into is R2. Now R2 has the same current as R1 running through it. It's going to point down. The current's going to go down. Now when I go through that resistor, I'm going to be going in the direction of that current. So this will be a negative I1 R2. And now I'm going to go through the middle branch from right to left. I run into the EMF 2, and I'm going from the negative side to the positive side. So this is going to be a plus EMF 2. And then I'm going through R3 in the opposite direction of the current that I have drawn, right? I'm going against that arrow, so that's going to have to be an increase. I've got that. I2 R3, that has to be equal to 0. All right, so that's one loop rule. The next loop rule, let's do the bottom loop. And let me just use the bottom loop, or use the same starting position. I'm going to start in the upper left-hand corner of the bottom loop, and let me go around this one clockwise. All right, so the first one I run into then is going to be that resistor R3, and I'm going with the current this time, so it's going to be negative I2 R3. And then I'm going to go through the EMF 2 from the positive side to the negative side, so that'll be a drop. That's going to be minus EMF 2. And then I'm going to go through the resistor R5 in the opposite direction of the current I3, so that'll be a plus I3 R5. Same thing for R4, plus I3 R4, and that's equal to 0. All right, now let me take a little digression here. Let me just illustrate what linearly dependent equations are. So I have these two equations. If I tried, let's just look at what the equation I would get from the outside loop is. Let me start at the same position. So I'm going to start here, and I'm going to go around this loop clockwise. So the first thing I would run into is EMF 1. Then I would have a drop across resistor 1. I would have a drop across resistor 2. I would have an increase across resistor 5. And I would have an increase across resistor 4. The sum of all potential differences has to be equal to 0. Now what happens if I just take the first two equations and add them together? So let's take this equation and just add them together. So I've got first equation, EMF 1 minus I1 R1 minus I1 R2 plus E2 plus I2 R3 minus, so this is the second equation now, minus I2 R3 minus EMF 2 plus I3 R5 plus I3 R4. That's equal to 0. Alright, this term and this term are going to cancel. This term and this term will cancel. And what am I left with? Well, I'm left with EMF 1, I1 R1, I1 R2. That's these terms right here. And then I3 R5, I3 R4. That's those two terms right there. So if I take the first two equations and add them together, I get the outside loop equation. That's what linearly dependent means. It means the outside loop equation doesn't contain any more information in it than the first two equations. Right? And if I wrote those three equations down and tried to solve them, I would not be able to solve for the currents. Right? I would get trivial things that said like I1 is equal to I1. All right, so I'm gonna erase that now. So we have two equations, we need three. The third equation is going to come from the junction rule. The junction rule can either be applied to the left or right junction. I have that left junction identified, so let's just use the left junction. Basically, I just look at all the currents that go in or out of that junction, and I say that, well, the total current that goes in plus the total current that goes out has to be equal to 0. So let's just call current that leaves the junction negative and current that goes into the junction positive. In this case, all of the arrows point away from that junction. So my junction rule would be negative I1 minus I2 minus I3 is equal to 0. There we go. I have my 3 equations that I can solve for my 3 unknowns. Let me go ahead and label this as junction rule. Okay, so now the only thing that's left is some algebra. And in this case, all of the resistances are different. So the algebra maybe looks a little bit ugly, but it's not actually that bad. What I typically try to do is I say, okay, well, I'm going to start with this junction rule. And what I'm going to do is I'm going to try to get this junction rule written in terms of just one of these currents. So I'm going to try to get it written in terms of just I1 or just I2 or just I3. Now, which one I choose basically depends on what other information I have. So if I look at the top equation, right, that's got current 1 and 2 in it. And if I look at the bottom equation, that has current 2 and 3 in it. So I could use the top equation to replace current 1 with 2. Get that turned into a 2, well, an expression that contains 2. And I could use the bottom equation to replace 3 with 2. And then this junction rule would just have I2s in it, and I could solve for I2. So let's do that. So the first loop rule, I'm going to rewrite in terms and try to get I1 written in terms of I2. So I'm going to do a little bit of algebra here. And I1 R1 plus R2 is equal to E1 plus E2 plus I2 R3. So all I've done is rearranged that top equation, took this stuff, moved it over to the right hand side, and then flipped the equation. So I1 can be written as this. And I've just separated these terms here so that the I2 is by itself. Okay, so there's 1. Now let me do the bottom loop rule equation to solve for I3 in terms of I2. I3 times R4 plus R5. This is just rearranging that second equation. EMF2 plus I2 R3. So I can write I3 as all right. And now take those and plug them into my junction rule. So negative I1 minus I2 minus I3 is equal to 0. Negative I1 is going to be this. And then I got a minus I2 minus I3. That has to be equal to 0. So this right here is minus I1. This is minus I3. Now the only thing I have in this equation in terms of unknowns is I2. So let's get that I2 isolated. I have 2 terms that don't depend on I2 at all, so I can move those over to the right hand side. And then I'm going to factor out this I2. Okay, so on the left hand side I have an I2 times all of the stuff. So this, and this, which is just 1. So let's do 1 plus all right, now I've got a negative sign I need to make sure that I keep track of there. And then I've got the other stuff that doesn't depend on, or doesn't have I2 in it. That's going to move over to the right-hand side. So I've got an EMF1 plus EMF2 over R1 plus R2, and an EMF2 over R4 plus R5. Alright, now I2 I can solve for. There's going to be a negative sign. Let's put that up here in the, well, let's just put it right here, I guess. So I've got an I1, or excuse me, EMF1 plus 2, and then an EMF2. And then just take that, divide it by this stuff here. There we go. There's I2. So that I2 then would be the current that runs through this middle branch. Let's just check and make sure that we are at least dimensionally correct. I know that in general, Ohm's law would be current is equal to a voltage over a resistance. So that means that I should have dimensions of voltage over resistance. Well, if I look at this term here, that's a voltage over a resistance. A voltage plus a voltage is a voltage. Resistance plus a resistance is a resistance. So that is volts over ohms. So that's good. Same thing here, volts over ohms, so that's good. And then down here in the denominator, I've got 1, which is dimensionless. Here I've got a resistance over resistance, resistance over resistance, so those are dimensionless as well. So the denominator is dimensionless. The numerator has dimensions of volts, voltage over resistance. So dimensionally, everything looks good. Alright, so that's I2. I1, then I would take I2 and I would plug it back into the equation that I had for I1, right, which is up there. So that's going to be E1. Oh, hold on, I have something misbehaving on me. There we go. So an E1 plus E2 plus R3 over R2 plus R2 plus R1. So get rid of that one. And then the I2 goes right here. So I take this, plug it into there. And then I have the same thing for I3. Some function or some calculation that includes I3. Alright, that's this one right here. So I'd be able to plug all of those. And if I had numerical values, it'd be even simpler. I would just calculate a numerical value for I2, and then I would take that, plug it in to calculate a numerical value for I1, and a numerical value for I3. So that's it. So that's an example of using Kirchhoff's rules. And we had to use Kirchhoff's rules in this case because of this EMF right here. If that EMF wasn't there, then we could actually have turned this into a single effective resistor and done it just like we did in example 1.